So I know the beam with its boundary conditions has complete fixity at the left end. There's no translation and there's no rotation. Over at point B, that beam has no translation. So those are going to be our boundary conditions as we look to satisfy and solve for constants in the second order beam equation. So down here, the boundary conditions, the displacement in the vertical direction at x equals 0 is 0. The slope at x equals 0 is 0. And the deflection at x equals 10, which is right over the roller, is also equal to 0. So again, notice we have three boundary conditions. So I'm just going to rewrite the second order beam equation with curvature over here on the left-hand side. On the right-hand side, right, that function right there is m of x that we worked so hard to find. And then it's going to be divided by EI. So what I'm going to have to start doing is just integrating this. So let's go ahead and integrate that function with respect to x. That reduces the order, and I end up with the slope equation. And what also is introduced along the way is the constant of integration C1. And at this point, we can use a boundary condition. Right? We know that the slope at x equals 0 equals 0. So if we go ahead and plug that in everywhere, I'm going to have a 0 right there. I'm going to have a 0 right there and a 0 right there. And I also know that, again, at x equals 0, that equals 0. So then I would find that C1 equals 0. So I'm going to integrate that one more time. And now I end up with x to the third and a bunch of x squareds and another constant of integration that comes out. And I'm going to use the boundary condition at x equals 0 again. And so plugging in, I know that v at 0 equals 0. That becomes a 0 again, a 0 and a 0. So I end up with C2 equals 0. And I still have one more unknown that's sitting in my equation. It's going to be F1. So to be able to solve for that, I'm going to use my other boundary condition, my third boundary condition. And so using v at 10 equals 0, I just go to my function and I'm going to plug in 10 for x. And I know that the deflection is going to equal 0. So now I've got an equation that has only one unknown in it, this F1, this red F1, the reaction at the roller. So at this point it's just math. And so my equation now changes. Just multiplying some of those out, and I've now one step closer to finding F1. And so I find that F1 is 87.5 kips. It's positive, which means that in the picture it was drawn in the correct direction. So I've got 87.5 kips going up. And so now I can just take that value for F1 and plug it back into my equation for v of x. And when I simplify, I end up with just a single clean equation for v of x. So all I have to do is plug in any value of x. Again, remembering that this is only for values of x from 0 to 10, only from A to B, from the wall to the roller. Right? That equation, that solution does not work on the right side of the roller on those last 5 feet, the 5 feet of overhang. So if I want to find the slope at the roller, I'm going to take that equation that I've got for v of x, and I'm just going to take a derivative of it. That's going to give me an equation for the slope, and I'm just going to plug in 10. And just keep in mind our units here would be units of kip times feet squared. So we'll get into a little bit more of the units police. We're going to end up with some units cancellation here. Again, slope is a unitless number. So that means on the bottom down here, E and I also has to have the same units of force times distance squared, which it will. Now we'll do the fourth order beam equation. You'll begin to see some of the differences between those two. Again, we're looking just at segment AB because what we're interested in is the roller rotation, right? The rotation of the beam right above that roller. So what we're going to end up doing again is analyzing the segment, right, from the wall to the roller. And so to do the fourth order beam equation, what we need is the magnitude of the distributed load, which is known as W. And on that segment of the beam from A to B, there is no distributed load. And we need our boundary conditions. And what do we know about this beam, again, in segment AB? Well, we also know that V at 0 equals 0. We know the slope at 0, again, equals 0. Right, over at the roller, I know that V at 10 equals 0. And now we have a new boundary condition, a force boundary condition. I know the moment at 10 feet, the moment inside the beam, is going to be equal to minus 250 kip feet. And that's going to give us our fourth boundary condition, and we need 4 of them. We'll discuss how do we know that that's the internal force, that's the force boundary condition that we know. Well, if we go and draw a free body diagram, right, which we've had before, and so we've got a force F1, we've got force over here, and then we've got a moment over there in that wall. And on the other side, we've got the applied load of 50 kips. All right, so there's our free body diagram. And so when we're talking about internal forces, we look over here at the left end, we would see that inside that beam, just a sliver inside the end, we're going to have internal forces. And clearly they're going to be the same as the red arrows, the external support forces. So those are all going to be unknowns. All right, let's take a little bit even closer look. I'm going to cut this beam. All right, I'm going to take out the blue saw, and I'm going to cut it not at a distance X, but I'm going to cut it just before the roller. And so we're going to end up with a picture that you see right there that just kind of popped up. So there's the 5-foot overhang. Right, there's F1, right, which is the force from the roller. And then just a sliver on the inside, we've exposed the internal forces. So if we look at summing forces in the vertical direction, right, we would see that the internal shear is going to be a function of that unknown force. So that's not going to be a known value or a boundary condition. So if we spin a moment right there at the cut, we're going to find out that the moment at 10 feet, right, again, just shy of 10 feet, is going to be equal to minus 250 kip feet. So there are the 4 boundary conditions that we need to be able to do this problem. And again, the fourth order beam equation doesn't care if it's determinate or indeterminate. It just needs 4 boundary conditions. The number of physical and force boundary conditions is going to be related to the degree of indeterminacy of the beam. So I'm going to just rewrite that boundary condition, the moment boundary condition, because the moment is equal to EI times the curvature. So if we just rewrite that, it's going to be EI times the curvature at 10 feet is going to be equal to minus 250 kip feet. So again, this is good only for segment from 0 to 10 feet, right? Just segment AB. And now at this point, it just becomes a little bit of a math exercise here. We've got everything lined up. We have our equation. Right, there's our distributed load W, which is equal to 0. So I've moved EI to the other side times the fourth derivative of V. It's going to integrate that. It introduces a constant of integration. And I'm going to integrate it one more time. Now I have a curvature equation. And so now it would make sense to evaluate that at x equals 10 feet because I know the moment at x equals 10 feet in the beam. We had that just a moment ago. And it's equal to minus 250 kip feet. So I'm just going to plug in x equals 10 into the equation right here. So that's going to be a 10. And this is going to be evaluated at 10, and it's going to give me an equation that looks like a times 10 feet plus b is equal to EI times the curvature at 10 feet. And I'm just going to plug in the value of the moment, or EI times the curvature. So there's my equation. I'm going to call that equation 1. I'm going to hold on to that. It's going to give me a way to solve for some of these constants a little bit later on. So now I'm going to integrate this thing again. And I end up with an equation. All right, I've gone back to this original existing equation right there, right, before I evaluated it at 10. So now I've got ax squared over 2 plus bx plus c is equal to ei times the slope. And I'm going to evaluate that at x equals 0 because I know the slope over there at x equals 0. And so I'm going to find that c equals 0. So that goes away. I'm going to take that and I'm going to integrate one more time, which is now finally going to get me to an equation for v. And there it is. I've got a times x to the third plus bx squared over 2 plus d is equal to ei times v. I'm going to evaluate that with my fourth boundary condition. Right? I know that the deflection at 0 is equal to 0. So if I just plug that in, I end up with d equals 0. So if I go back and look at my equation now, looks like ax to the third plus bx squared over 2 is equal to ei times v. Right? I've found that that's equal to 0. So I'm going to evaluate it now with my fourth boundary condition at x equals 10. So if I plug in x equals 10 everywhere, right, I end up with 10 to the third right there. I end up with 10 squared. And over on the other side, I end up with v evaluated at 10, which I know is equal to 0. So I've got just one more equation with a and b in it. I'm going to call that equation 2. So I've got two equations. I've got equation 1 and equation 2. So I have a system of unknowns. So I'm going to take equation 1, which is above, and I'm going to multiply it by minus 1/2. And so that gives me an equation that I can now add to equation 2. And so you can see that the b times 1/2 is going to cancel. So if I then add those two equations together, I end up with an equation that has only a in it. And I just solve for a. So I'll go back and now use the answer for a. And I'm going to use it back in equation 2 right there. And so that's going to tell me that b is equal to a, the negative sign right there, times 20 over 6. And so that's going to be plus 37.5 times 20 over 6, which is equal to plus 125. So I have both constants solved for. So if I just slide back up here, right, this was the equation that we were working for. And so all I'm going to do is just plug in my values for a and b now that I have them. And so if I do that, I'm going to end up with an equation that looks like v of x is equal to 1 over ei and minus 37.5 over 6 times x to the third plus 62.5 x squared. And so we have the exact same answer we got from the second order beam equation. So this is a match. And so we would obviously get then the exact same slope if we took the derivative of that. So answer by second order beam or by fourth order beam, you'll end up in the same place. Fourth order beam has a little bit more math involved with it, a little less engineering. Second order, you need the equation for the internal moment, which causes you to use a free body diagram.